Welcome everybody to this month's Iowa Nutrient Research Center seminar. We're really fortunate to have Dr. Chris Jones. That's a research engineer with IIHR-Hydroscience and Engineering talking to us. First today, about 20 to 25 minutes, and then we'll have Dr. Brian Gelder, that's a manager of research at Iowa State University, talking to us as well. For those that didn't get a chance to see the seminar last month, Dr. Alejandro Plastina, Dr. Marshall McDaniel talked about soil health and economics. Those presentations are archived on the Iowa Nutrient Research Center website, so please go and watch those. So with that, I will turn it over to Dr. Jones.
Okay, thanks for the invitation. I have some slides to show you today, and you should know that I'm presenting on behalf of several people here today. And so I do post the slides to all my presentations on my website, and I keep my website pretty active. And so you can see that presentations page there on the menu. And so if you're interested in these slides, they're already up there. You can go get them. And there might be some links in the slides that you would like. And so a little bit about IIHR. We're sort of headquartered in the Stanley building there on the banks of the Iowa River here, downtown Iowa City. Not all of the staff and faculty are in there, and I'm not in there either. I'm in Trowbridge. But the Institute's been at the University of Iowa for 102 years. Pretty world-renowned research institute for education, research, and public service focusing on fluids. And so we really only have a handful of peer institutions, one being the St. Anthony lab in Minneapolis and a couple others in other countries. And so research staff, we have about 51 right now, faculty affiliates and PhD research staff. I'm the latter. We have professional staff of 49. This includes a number of different people and types of people, types of expertise. What you're looking at there is our shop guys. They work on building these physical models for faculty and then for outside people that need that sort of thing. Right now, we have about 87 grad students affiliated with IIHR and 12 postdocs. And there's a group that goes to India every year, and that's what you're looking at there. And so underneath or beneath the umbrella of IIHR is a flood center. And so a lot of people have heard of the flood center, but haven't heard of IIHR. The flood center is a subset of IIHR. And so Vitek Krajewski is the director of the Flood Center and has been for a long time. Two other people in this photo, Gabriella Villarini, past director, and Larry Weber now is a past director, and he's the director now as well. And so Gabriella is still here as faculty. And, one of the main work products the Flood Center has generated since their inception is the Iowa Flood Information System. And so this is that network of bridge sensors around the state that communities can use to help, evaluate their flood risk at any time of the day, any time of the night. Very valuable tool for a lot of communities around the state of Iowa. And so as part of that, after the development of the Iowa Flood Information System, it was thought that we could use a water quality network as well. And so the Carver Trust funded the creation of the Iowa Water Quality Information System, which I'll talk about a little bit here in a minute. But the water quality sensors that are deployed around the state of Iowa, there's about 70 sites right now, feed into the Iowa Water Quality Information System. So some of these sites, the equipment has been funded through the Nutrient Center. We also harvest data from USGS. We have a number of sites that have been paid for by ARS. They're in Ames. They own the equipment, and then several sites funded through the Iowa Watershed Approach Project. So all in all, there's about 70 sites. At almost all the sites, we're measuring nitrate, nitrogen. A subset of sites, we're measuring those other parameters that you can see there. And so the Water Quality Information System is where you can go to get the data, and this is really quite an incredible tool. Ibrahim Demir, a faculty here in informatics, developed this. And so if you're not aware of this, I'd really encourage you to go take a look at it and see what water quality is in the state at any minute of the day. And so what I'm going to talk about today are some projects that resulted from the Nutrient Center money. And so the Nutrient Center funding here funds the maintenance and operation of the sensor network. And we have published some papers based on, the overall data generation that's resulted from that. But the INRC association here with us has resulted in quite a watershed, if you will, of projects that we've been able to get funded. And so the biggest one, of course, is the Iowa Watershed Approach Project that's now ended, $94 million funded by the Housing and Urban Development, and Iowa State got a fair amount of that money as well. And of course, we had the target watersheds where we paid for practices that would improve water quality, but also flood resilience. And you can see the targeted watersheds there, that they were picked based on disaster declarations and then the percentage of low and moderate income housing. And so that's just ended here in the last 6 months or so. Another one that has just ended recently is the big data project we had from the Midwest Climate Hub. And so that funded the development of this Upper Mississippi Information System, which is intended to be a companion system to the Iowa Water Quality Information System. And so our intention with this is that this would be a clearinghouse for data. This is ongoing. It's going to take years to get this, to be a real, to get it on the level of the Iowa Water Quality Information System. We're going to really need a lot of participation from outside parties. And so there's some real-time modeling that's going to be a part of this. Every HUC 12 in the Upper Mississippi River Basin is going to be an ongoing SWAT model. Phil Gassman over there in Ames is doing that. And so that's just a little schematic of that. And so some more recent things that's come out of the Nutrient Center funding. Craig Just here, faculty member, has had a couple of projects funded that have married up to the Iowa Water Quality Information System and the sensor network. The first one here is this flood first approach to water quality improvement, funded by EPA, $770,000. That was focused on these flood mitigation and nutrient reduction wetlands in the Mud Creek watershed, which drains to the Cedar River. The town of Vinton is in this watershed. They have a wetland that they use to treat their wastewater that was not part of this project, but there's a picture of it. And so there's the watershed. You can see Mud Creek in black, the Middle Cedar watershed, of course, where there's been a lot of work done, outlined in blue. And you can see our sensor there in the creek. That's the outlet of the wetland. And so here's some more shots of the Mud Creek deployment. And you can see the wetland there with the dam on the left. Our sensor set up there with the solar panel and the data logger and the battery and so forth in that dry box, and then the sensor down in the creek. And so actually in that watershed, we have 4 nitrate sensors deployed. They're still over there, even though the student that was working on this has largely completed her work. And so Craig, Just, and the student were looking at both nitrate removal in the wetland, and also peak flow reduction. And, we can see there that in that constructed wetland, we call it the Gelder wetland, nitrate reduction about 60% with the hydraulic residence time of 23 hours, 27%. 11 hours, that really is consistent with the science assessment that was conducted for the nutrient strategy by the science team. As far as peak flow reduction over there, what they're seeing in an NRCS type A design storm, about 15 to 26% based on, the bottom end there, 2-year storm, the top end, a 500-year storm. And then a type D design storm, 9.6 to 17%. With all these projects that we do that I'm going to talk about, we evaluate sensor accuracy based on comparison with grab sample results. Those tests or those samples are analyzed at the State Hygienic Laboratory here. And so Ashley, that's a student here, did that as well. And in all of these projects, we find the nitrate sensors to be very accurate and very reliable and very consistent with lab results. And so her thesis is here at this link. And like I said, if you want that, my slides are posted. You can go and look at the thesis this student wrote based on this project. Her name is Ashley Knudsen. It was a master's project. The second project of Craig's is this Gulf of Mexico program cooperative agreement connecting rural and peri-urban farmers to demonstrate and disseminate innovative nutrient and sediment reduction practices. This one a little over $1 million. Again, married up with the sensor network and the Iowa Water Quality Information System. This project's at the Johnson County Poor Farm, where we have wetland, terrace, and controlled drainage. And you can see the constructed wetland there. The Johnson County Poor Farm, of course, I think everybody knows what those used to be. Now it's managed by an NGO, the Iowa Valley Resource Conservation and Development, and they produce vegetables for food banks and other folks here in Johnson County. And so their goal focuses on those 5 bullet points there. And so I don't have any water quality data to show from this yet, but that project is ongoing. The sensor is there. It is up on the Water Quality Information System, and so it will measure the effectiveness of practices implemented at that site. One of the more interesting things we've been able to do as a result of our experience with the sensors is this boat deployment. And so we had a student get his master's degree on this. You can see him there, Matt Mulemans. And what he did is he worked with the shop guys to construct this apparatus to continuously measure nitrate and also some other parameters, pH, DO, and so forth, with the equipment mounted on a boat. And so he could drive around in a boat, geolocate the samples on his laptop right there in the boat, and continuously collect samples and aggregate the data. And this was really a fun thing for us to be involved with. The IIHR has several boats, and we had a jet drive outboard that he could use on a John boat. And so with that, he was able to navigate easily in shallow water and rivers without having to worry about breaking the prop off. And so what he did was he took the John boat, mounted with the water quality equipment, and made 4 trips each up the Iowa River and the Cedar River. And so that basin there, 32,000 square kilometers, it's 20% of Iowa, intensely cropped, high nitrate in both streams. And this is our second largest internal basin. And so, as I said, he made 4 trips up each river, and you can see there the 4 trips. One was in May, one was in June, one was in July, and one was in August of 2018. And so those lines there are the nitrate concentration based on the distance from the outlet at Wapello, Iowa, down in southeast Iowa. And so you can see not much variation in nitrate, except in August when we see a fair amount of processing in the river. These letters at the top here indicate where tributaries come in. And so this SF, that's the South Fork. And we can see how nitrate jumps up in the Iowa River after the South Fork of the Iowa River comes in. No surprise, everybody knows about South Fork and the high nitrate. Also, we see Coralville Reservoir here, and we can see some things happening in the reservoir. And then down here where the Cedar River comes in, drops the nitrate in the Iowa. And so then he also did the Cedar. And so we can see here the 4 trips up the Cedar. Down here, mile 0, that's Columbus Junction. And so we see here where the West Fork of the Cedar comes in, we see some drops in the nitrate concentration. And so the headwaters of the Cedar coming out of Minnesota, the West Fork, of course, coming to the Cedar from the west, tends to be lower nitrate. And so we see some drops there. An interesting thing here is we see an increase in the nitrate. Here, this is Wolf Creek. This is the Middle Cedar. And so that's intensely farmed there with a lot of tile. And so we see in the month of August here, some increases in nitrate due to that, to the tributaries in that area. And so we don't see nearly as much processing in the Cedar River as we did in the Iowa River, which is sort of interesting. Matt also took the boat up to Storm Lake and drove around Storm Lake, and you can see this little thing up here. That's what they call Little Storm Lake. It's basically a wetland, and you can see how the nitrate is quite high coming in, and it gets attenuated as the water goes through this wetland before it enters Storm Lake. He also collected pH data up there, and you can see this might inform where the algae blooms are in Storm Lake based on the pH level. Again, he also, like Ashley, did some comparisons that evaluate the sensor accuracy versus lab measured samples, and the sensors just continue to be very reliable for us. And so all this, Matt's thesis is the link here. And again, you can get this off my website. We did publish a paper from this data, and I feel kind of bad we only published the one paper, because this was really some really fun and valuable work, I think, that Matt did. We're continuing with this. We've got a project funded through the Corps of Engineers to evaluate nitrate attenuation in the headwaters of Red Rock Reservoir. Keith Schilling is the PI on this, and that's ongoing. We're doing some work now, and so this is some of the work that's been done this fall, taking the boat out there and running it around with the nitrate equipment. So one other thing we've done here in the last year or two here, I did this paper with Dave Swertney. Some of you may have heard of him. He's the director of Cheek, the Cheek Institute here at the University of Iowa, where we evaluated the sensors and their implications for municipal drinking water. We looked at the sensor data that were in the rivers at these 5 spots and compared them to the finished drinking water from nearby water utilities, public water supplies. And so this graph here is a time series data for the Iowa River and 2 water utilities here in Iowa City, the city's water utility, and then the University of Iowa also has a water treatment plant. And so we compared the river water with what the finished water was coming out of these treatment plants, because the sensor data is continuous every 5 or 15 minutes, whereas the municipal water supply data is not continuous. They're grab samples, sometimes daily, sometimes monthly. And so we were curious what the potential was that these systems were violating the nitrate standard based on the frequency of their sampling. We also looked at Ottumwa, and you can see there Ottumwa was just reporting monthly nitrate data. There's the Des Moines River data in brown, and so at any rate, we looked at these relationships. And so, for example, Ottumwa, if the river was at 10.8 milligrams per liter, that's PWS6, they probably would be above 10 on their finished drinking water. And so we can see here, the Des Moines River down there is above 10 quite a lot. And so the potential for drinking water violations is pretty high based on their operating permit and how frequently DNR was requiring them to report nitrate data. And so we can see this PWS2, that's the university's treatment plant here in Iowa City. If the river was 10.3, then the finish was likely to be above 10. The university does have nitrate removal now, and so that's good because they probably were violating from time to time without anybody knowing it. And so we evaluated the cost of these sensors versus grab sample monitoring. Really, systems like Ottumwa and the university here should probably be monitoring on a daily basis. To do that, about $15,000 a year. To buy a sensor, $25,000, and that would be good for several years. And so we really think that DNR should take a look at this in terms of compliance monitoring and helping some of these systems get these nitrate sensors in their treatment plants. Another thing, we don't just measure nitrate, we measure turbidity. And so because of that, we got to be part of this Polk County Water Trails project, which you may have heard of, 9 sites in Des Moines. And so this was funded. I was the PI on this. The objective was to quantify a relationship between turbidity and E. coli, another potential pathogen. So users of the water trails system would be able to get some idea of what the risk was for contact recreation. And so this was one of the sites at Des Moines River. The equipment's in this doghouse there, we call it, to protect it from vandalism. One of the problems we had with this project, we have 2 main problems. One is the E. coli is always high in some of these streams. And so these bar graph shows the percentage of time exceeding the recreational standards at the 9 sites. The other problem we had, it was really dry during the entire period that we conducted the project. And so we tried to look at some event samples. And so this graph shows rainfall in Des Moines there. The blue is a discharge on the stream at Walnut Creek. The brown is turbidity, and then the dotted lines are E. coli and Enterococcus. And so we thought we might learn something from these events, but it turned out these events were always different. There's another one. And there's a third one on Walnut Creek, and I won't spend too much time on this. But at any rate, we tried to use the accumulated data to develop a relationship between the turbidity and E. coli. And Elliot, our grad student, Elliot Anderson, worked with us on this. And so I looked at this graph and I immediately thought this looks like the relationship between nitrogen inputs to a field and corn yield. And so, you look at it and you can say, well, I see something, but, it's not very definitive. And so what he did was he developed these logistic models based on the collected data. And so what we have here is the likelihood of the water exceeding the recreational standard of 235 colonies per 100 mils. And so all these data points are at the bottom are less than 235. All these at the top are greater than 235. And so we can see here, based on his logistic model or logit model, that at a turbidity of 55.7 on the Raccoon River, there's a 50% chance that the E. coli exceeds the recreational standard of 235. And so what we'd like them to do going forward is fund the creation of a web page that would be on the water quality information system. Their turbidity data would stream in at real time. Somebody could go to the web page and see what the likelihood of the E. coli being above 235 is before they go throw their kayak in the water. So whether or not they're going to do that or not, I don't know, but this just finished. We just gave them a final sort of presentation a couple weeks ago. But again, this project married up very nicely with the water quality information system, and their sensors will be part of the nutrient center network for the foreseeable future. So that's my last slide. Again, just some of the projects we've done here. The nutrient center has been a great resource for us on a number of levels, and it's enabled us to, we've really been able to leverage the work here, the nutrient center work, to a number of really fun and valuable projects.
Yes, thanks, Chris. It was great to hear about how things have been leveraged in the range of projects that you've done. As I get Brian's presentation up, is there one or two quick questions for Chris? Somebody could unmute as well if they want it online, or if there's a question from the audience in the room here. Anybody online? Otherwise, after Brian, we could go to some questions too. I will ask one. Are you available if people, have questions about use of the sensors, how well they work, and that kind of thing? Or
sure. Yeah, absolutely. In fact, I feel kind of bad. We have never tried to publish a paper based on the performance of the sensors, and so yeah, absolutely. There's two staff members that do the field work. Tom Steffler, who's been with us for a long time and is a great guy, and we've come over there to Ames, I think, and helped on a couple projects, and I can't remember if it was Kay or somebody else that. Oh
yeah, Kate went out when they were setting it up.
So yep. We're completely willing to come and work with people, and if you're interested in deploying a sensor for a project, by all means, let me know.
Okay. All right, I'm going to turn it over to Brian.
All right, thank you. Thanks, Chris, for not making me feel bad. We don't have this published yet. It's still kind of a little bit of work in progress. First, I want to thank or acknowledge my co-worker on this, Forrest Williams, who is a master's student with Peter Moore over at NREM, and now he's just completing his master or his PhD with the University of Massey in New Zealand. He remote worked throughout the pandemic from the safe spot in New Zealand during most of the pandemic on this. And he's a lot of the data analysis, the Google Earth Engine data analysis behind this project. So I'm kind of a mud scientist. I like to work at the interplay of soil erosion, runoff, water quality. So I title a lot of my stuff mud science. Kind of consider myself a mud scientist, kind of in my email tag. And why should the Nutrient Research Center be interested in remote sensing? Primarily, monitoring is a really good solution for a lot of things. Remote sensing is a really good solution for data acquisition, low-cost data acquisition on large scales. When you want to try and gather things like practice data, like we're trying to do like this, remote sensing is really your best option to try and do things like this. Often, you hear lots of people always saying that you can't manage what you don't measure, and the remote sensing is an economical way to measure this, doing things consistently. One of the problems with the human observers is we get biased in most everything we evaluate, and remote sensing is at least you can at least usually quantify the bias, and it's usually consistent in that way. It also allows us to look at looking at practice adoptions. We can actually scale this over time now, and then you can start looking looking, one of the things we like to do is seeing what encouragement works. Have some of the social scientists join us in on what do we see? Do we see any trends from these practices over time? Again, water quality, that's a lagging indicator of change. And these tillage management indicators just allow you to get a better idea of what should be coming down our streams and rivers in the future as we look to improve that water quality, mainly because tillage practices definitely influence sediment losses through erosion processes, and then they've also got follow-on through phosphorus loss. And our surface water balances influenced by tillage practices, again, influencing the nitrogen loss processes as well. Why am I specifically interested in it? I do the daily erosion project along with Rick Cruz in the Department of Agronomy, the Iowa Water Center leader as well. And what we do in this is we estimate precip runoff, sheet and rill erosion daily for Huck 12s across kind of the Western Corn Belt. You can kind of see our current domain there using the WEP, the water erosion prediction process hill slope model. And this is just essentially a large scale model implementation using a number of high resolution georeferenced inputs to essentially every day give you an estimate of what happened soil erosion wise across that domain. So if it doesn't rain, well, there's snow melt, you actually see something, but otherwise it's not raining or snow melting, you really don't get to see a lot. How does that work? We bring together our NextRad, our LIDAR, our Sergo soils, and our land use and management, which is what one of the end results of this project has been, is to go into our WEP erosion model, generating our estimates of crop growth and canopy coverage, and our estimates of soil runoff and erosion that comes from there. Why do we think this works? The key process is that residue cover reflects a little bit differently in the middle infrared than soil and green vegetation. There's better ways to do this than what we have available to us. We use Landsat, the Landsat series of satellites, and the Sentinel-2 satellites to do this work. These satellites give you great coverage all the time, or great coverage every couple of weeks across an area, but they don't give you spectral resolution. If we really had hyperspectral sensors, we could actually do a little bit better job in this than we have to do with the current satellites that we have available. So the Iowa Nutrient Research Center funded a project mid 2015 to 2017 where we collected data from 251 locations, both on private farmland and some Iowa State farmland across the state to help validate this model, which is this project was kind of a follow-on to some PhD work I had done back in the mid 2000s to see how things were working. What we did was collected a lot of pictures of residue cover on the soil, pretty much 5 locations per field, and then had students go through and visualize a grid on these images and count whether they saw residue or soil at each one of these locations, as long as there were no plants actually growing at that location. And to do this, we essentially come up with a field average residue cover, and we buffer those field boundaries that we were assessing inwards by 30 meters to reduce edge effects from the imagery. So here's kind of where our distribution across the state was, area around Ames, some north central Iowa, central Hamilton County, Jasper, Polk County, and we had a good number of collaborators down in southeast Iowa, and just a little scatterings out in western Iowa where we were able to get some field samples as well. What's the process we use to do this? We use kind of a combination between local machine management and Google Earth Engine analysis, and that's what really allowed us to take the initial analysis that we were having some difficulty getting enough data analyzed for, to go into the Google Earth Engine and be able to analyze pretty much the entire stack of Landsat data everything that's been collected in a reasonable amount of time. If you're ever doing remote sensing now, these cloud services are the way to go. They just allow you to analyze so much more data in such a cost efficient and time efficient manner. So we did a lot of that work. We did, some of the ground truthing work and the final data analysis on local machines, but then most of that work was fed to Google Earth Engine to do that processing. What were we evaluating things for? Google Earth Engine allowed us to do some new things. We investigated some new indices or multiple indexes. These aren't really new indexes, but the combinations and interactions between some of these things. We use what's called the normalized difference tillage index, NDTI, for residue cover, which is some shortwave infrared ratioing. We used NDVI, your vegetative index, for estimating green vegetation. And green vegetation is a problem because as plants grow up, to the index, it looks like residue cover. So high amounts of green vegetation also make the systems think there's lots of residue cover out there. So you don't want to be looking at really green fields thinking there's lots of residue cover out there. And we also looked at a moisture index for removing overly wet soils. Again, you have problems where the wet soils have lower index values. That biases the index lower compared to a dry soil. So we're looking for kind of the optimal combination of indexes to look at here. You don't want fields that are too green. You don't want fields that are too wet. You want to get images from those fields at the right time of the growing season. So what we ended up with was an approach where we evaluated kind of at the sensitivity of filtering image. Filtering image data to find images that are not too green, they're not too wet, and they're going to allow us to give us that great estimate of residue cover. So you can see on our right hand side, we kind of looked at all of our data sets. As you go through time, the tillage index definitely really starts to increase once the crops start greening up. Same thing happening with NDVI, that is those crops greening up. And our moisture indexes, our soils dry out, as the sun gets stronger, you get more drying power, and we start seeing a decrease in that. And so we're looking kind of for this sweet spot, trying to collect as many images as we can, process as many images as we can in that nice portion of the year, that late April, May, early June timeframe. But that's going to vary by field. Each farmer is managing each field individually based on the appropriate conditions and how fast they can get out and do the work in those fields. All right. So when we looked at all the data, we found out that as you throw out more images, saying they're too green, they're too wet, you increase your accuracy. That makes sense. You throw out the outliers. But the problem is, if you throw out, we saw increases in, throwing out 40% of the data. But when you throw out 40% of the data, you really lose coverage on about 40% of the fields on an area basis. And that's not really what we want to do. We want to try and keep as much data as possible. So get an acceptable amount of accuracy, but also get a very good amount of coverage. So we looked at, what kind of a threshold gave us the best numbers. And our assessment was that about 80%, throwing out about 20% of the images gave us the optimum trade-off between coverage and accuracy. Giving us about 85%, 86% coverage of the corn and soybean acreage every year. So pretty much we're going to get data about 6 years out of every 7 on an average agricultural field. If we look at this, try and estimate, use these indexes and try and figure out how do we estimate residue cover. And most of the time people will just throw it in and what's your best R squared, that's your best relationship to to predict these things. But the problem is when you do that, we often end up, and you'll see that in the next slide, estimating too much residue cover. The best fit R squared overestimates residue cover at that low end quite a bit. And that's where the soil erosion action is happening, these low residue cover fields. So we want to get the best estimate we can of how many low residue cover fields there are in the state. So we took a modified R squared approach where we anchored our intercept to our 3 lowest fields that we had in our data set. So our 3 fields with the lowest amount of residue cover, we use those to anchor our intercept and essentially lower our regression equation. It resulted in a little bit lower R squared and mean absolute error, but it did substantially lower the intercept of our regression line. So you can see that in here. You know, we do a much better job. Here's our anchored, think in green, and we've got our normal, our best fit R squared in red there, where we've got a much higher intercept. There is no zero on the end. There is no zero on the NDTI, means 0% residue cover. You can get slightly negative NDTI values on low residue cover fields, maybe down to 0.02, 0.04. So that's not some magic number we're trying to hit with our regression. On the right panel, you can also see, you know, the impact of removing those really green and really wet fields has on improving our R squared. So those are fields that were thrown out just because the imagery for those time frames when we were making those estimates was just either too wet or too green. You can see kind of down on the bottom how these things performed on you know, all crops. So that would be corn and soybeans, and we did have a few alfalfa fields. We had about 3 alfalfa fields in there in the mix as well. Corn fields generally performed a little bit better than soybean fields. That's, you know, generally, I think we got a better estimate. We get better estimates of what high residue cover looks like in corn fields because it's very hard to find a high residue cover soybean field in the middle of May or June. So after we had some pretty good, after we found these pretty good results, it was pretty easy to send Google Earth Engine out and say, give us a map of soil residue, of residue cover across. We pretty much set it to the eastern edge of Illinois, and then west to the edge of Nebraska, kind of for our similar to our DEP estimating domain. And so we now have residue cover estimates. These are 2021 estimates, and you kind of see, you can start to see some of the differences in major land resource areas that were popping up that are, you know, pretty interesting. They seem to, and they also, luckily, they also seem to correspond with my own experience of what's going on in the fields that I've worked in and I've observed. You know, getting it a little closer to home, we've also calculated a median residue cover. So for the 2011 to 2021 timeframe. And that's really, you can really start to see what's going on. We've got the major land resource areas overlaid on there. And one of the things that, you know, I had not observed, but, you know, it's kind of as a soil management person made a leap out to me was in most of these major land resource area boundaries, you do not see any kind of sharp change in residue cover from one side of the major land, the Des Moines lobe to the northwest Iowa plains or to the Iowa erosion surface. There's no sharp cutoff. Farmers don't switch their tillage practices on one side of the soil, one soil MLRA to another. But we do notice that, you know, as we move down into the Loess Hills area here, there is there is a sharp break in the tillage practices that farmers are using, the residue cover that's being left when you move from the lobe to the Loess Hills. And that makes, I mean, knowing how those soils work in the different areas, that makes sense. But it's just an observation I hadn't seen before between different land resource areas. You can also still see, the Missouri River floodplain doesn't show up as its own major land resource area, but you can still definitely see there's also a big increase or decrease in residue cover levels once we get out to those really flat, low-lying fields on the Missouri River floodplain as well. So it's been doing, I've been very happy as we've been starting to get some projections, not projections, but estimates out of the model over the last year, that they correlate really well with my experience. We've also had some collaborators in the Green Bay, Wisconsin area that they've got annual residue cover photos, and we've had them do some analysis on what, and I've done some analysis on what they see in the field versus what we estimate on these from the satellite, and it works well over in the Green Bay area as well. So we're continuing to expand the domain and our confidence across this area, looking what's going on to generate continuing better products. Starting to look at year by year analysis. So major land resource area by year. You can see our Des Moines lobe by far the lowest residue cover throughout time. Our other northern more northern MLRAs are also below the mean for the state, whereas most of our southern or more sloping ones are typically our higher residue cover. Also makes sense from regulatory standpoints, and that's going to be where more of your HEL land is with required conservation plans as well. So last little bit, we did zoom into kind of the Gelder, the Gelder farm around Kamar, Iowa. We do still have some impacts going on that we think there's a soil signal in this that we still haven't been able to fully diagnose. When we look at fields in this area, there's lots of closed depressions, and you typically see that the low depressions, the estimates are too low in these areas. On the ridge tops, the summit positions, our estimates are too high in these areas based on what we know for an average field residue cover and variability within a field is. So we think we've still got some additional work on this area. And we also think this process can, be applied to some other remote sensing application. This process can also be informative of things like cover crops and other practices that we want to eventually move on to try and do some remote sensing on as well. So that's wrapping it up.
All right. Thanks, Brian. Okay, I have two questions
Sure.
for you. One is your information available? Do you have the maps or some of that available?
They would be available through me right now,
Okay.
because we're still we've sent it off for publication a couple times, but have ran into a disagreeable editor both times, I think.
Okay.
So
Okay.
we're comfortable with them disseminating them, but we don't have them peer review published yet, so we don't have them out on.
Do you have them on a
on the state side.
repository?
Yeah.
Okay,
Yeah.
that's what and then the other thing is, are you going to, or how much would it take to continue to look at as we move ahead with years? Because you have that summarized through 2021.
So running these, now that Google Earth Engine has done what they've done, revolutionizing clouds, running these scripts additional years would be a really low cost effort.
Okay.
Incorporating new training data would take quite a bit more work,
Okay.
but just keeping the algorithms running is pretty good dollar now.
Okay,
The question online.
okay, there is, right.
Are you getting that up? Brian, 2 slides back.
I'm not seeing the question, so you might have to.
Yes. So how do regional HUC-8 tillage comparisons compare to other methods such as Optus?
How would our HUC-8 estimates compare to things like on an Optus tillage estimate? I have not done that analysis to see how they would compare in terms of accuracy on a side-by-side basis. I have enough concerns with the way Optus has done things that I haven't done a comparison with Optus.
Real quickly before the next question, if anybody needs a CCA CEU, folks may have seen that we applied for credits for this. So a soil and water credit, email K Stefanik, KCSTEFAN at iastate.edu by tomorrow noon with your name, the name you entered to watch the seminar, and your CCA number. So All right, Malcolm, other
Yeah,
questions?
but if you go back to your second last slide.
So it'd be like the MLRA slide.
Yeah, well, the graph of the residue.
Per
It
year,
was-
yeah.
It was pretty cyclic.
Yeah.
So what's the cause of that?
What's the cause of that? Well, so if you remember what it looks like, it bottomed out on the statewide. It bottomed out about 2012, 2013
Right.
as the lowest residue cover. That's also record high corn prices at that time. I'm interested to see what's going to happen because we're entering another period of record high corn prices to see whether this goes back down at this time. Some people think, well, corn's got more residue. You should be observing more residue cover, but oftentimes farmers will go continuous corn when you have record high corn prices. And a lot of farmers, especially in the Des Moines lobe, till very aggressively when they're doing corn on corn to remove that residue. And oftentimes leave quite a bit more residue when they're planting soybean.
Yeah, that's what I thought it was.
So that'd be great to investigate.
Any other questions? Otherwise, we have reached, oh, Sean Richmond had a question. You can unmute yourself, Sean.
Yeah, thanks, Matt. Hey, Brian, so a question on your MLRA slide again. So it appeared to me that as of 2021, each MLRA had greater than 30% residue coverage. Is that correct? I mean, I'm just wondering the implications of that. I mean, that's basically saying that is that saying the entire state was at some form of conservation tillage or greater? Conservation tillage being defined as 30% residue cover or greater.
Yeah, so that would, based on this regression, that's a correct assessment.
Okay.
And I don't think that would be, in the Des Moines lobe, that would kind of mean about half of the fields are going to be in that category and half of them aren't going to be, which I think would probably be a fair assessment of even the Des Moines lobe at this time.
Gotcha.
We've got some, as I said, we had to pin our lower residue cover estimates by those 3 lowest performing fields we had, and that's going to have that's going to have some impact on that.
All right. Thanks.
All right, it is after 4 o'clock. So in the interest of time, we'll cut it off there. I want to thank Chris for his presentation and Brian for his presentation. And these will be up on the Iowa Nutrient Research Center website. So you can go and look at those and watch them again, or tell a friend to watch them. And be sure to tune in next month. Stephen Hall with Iowa State University and Justin Meissen with UNI will be talking about prairie potholes and then prairies. So we're moving from monitoring or remote sensing to thinking about prairies and prairie potholes. So tune in next month. So with that, everybody have a great rest of their day. Oh yeah, virtual. Yeah, let's thank our presenters virtually.